let me start recording. This is section 8.1. So we've got 4 more lectures, including today. Sorry, 4. And so the idea is we're going to look at these limits of functions for 2 lectures. And then we're going to use limits of functions to finally prove some results about the exponential function, the logarithm function, and then sine and cosine. Okay, so those are the 4 remaining lectures. Two on limits of functions, and then 1 on the exponential, and the final lecture on sine and cosine. Okay, so the key point is that okay, I hope my screen's back. The key point is that before we looked at sequences of points. So this is sequences of points. Okay, we might have had a function around. So we might have looked at the sequence of function values of these points. Okay. For example, we have one really useful theorem about this, which, remember, it says that this is theorem. I actually looked at the number, so I know it's 5.4.7. It says that if f is uniformly continuous and our sequence xn is Cauchy, then the sequence f of xn is also Cauchy. Okay? So I'm just reminding you kind of how we used sequences and how we looked at functions of sequences. Okay, so the big difference today is that instead of the point changing, the functions are going to change. So now we are going to look at sequences of functions. So let's suppose that Fn maps from some domain to the reals. And we have one of these functions for every natural number. Then the sequence Fn, well, okay, that is a sequence of functions from A to R. Okay. Not much to the definition, just pointing out that now we're letting the functions change instead of the points. A first thing you want to do when you've defined sequences is define what it means to converge. So, well, let me ask for suggestions. What should it mean for a sequence of functions to converge?
Maybe
oh, sorry.
I was gonna say is like as you, it's kind of imprecise, but as you go towards infinity, the functions are almost indistinguishable from each other.
Mm-hmm. It's a great suggestion.
I have an idea.
Okay, Daniel?
Maybe we could do kind of like a Cauchy type thing where after a certain point the difference in Fn and Fm greater than some value is less than epsilon for any point in the domain.
That's another great idea. Yep. Okay, so that's interesting. Both of you have described uniform convergence. Okay? And that is going to be our second definition today. Our first definition is an easier condition than uniform convergence. Okay, so hold those thoughts that you gave me. That's great intuition. That's uniform convergence, and as we'll see in our final 4 lectures here, uniform convergence is way more important than the convergence I'm about to define. Okay. The weakest notion of convergence we could have is convergence at a point. Okay, so one idea would be if this converges at a particular point. Okay, so we know what it means for right. So now if you plug a particular x into all these functions, you've made your sequence of functions into a sequence of points, and we know what it means for a sequence of points to converge. Okay. So let's give the definition. This is of pointwise convergence. Okay, let's let Fn be a sequence of functions from A to R suppose F also maps from A to R, then Fn converges to F. Oops, I want to put that in red to emphasize that's what I'm defining. And then let me emphasize this is pointwise convergence if for every point in the domain this sequence of points Fn of x converges to f of x. So again, you look at any particular point in the domain, eventually the sequence converges to f of x. Any questions about that definition?
So in this definition, our deltas can depend on this x we pick.
Yeah.
Okay.
So we're okay. So we're talking about sequences. It's really our capital N's can depend on the point.
Okay.
Okay. So actually, let's do that. Let's do this. This is a lemma in the book, but it's really just a restatement of the definition. Okay. So in the book, this is lemma 8.1.3. So the sequence Fn from A to R converges still pointwise. Okay, and I keep saying pointwise because we're going to have another more important definition soon. To this function f from A to R. Yeah, for now let's just unpack we're just unpacking that definition. What the definition said above is that for every point we converge to f of x. Okay, so now let's just write that in. If for every x in the domain, and now what does it mean to converge? It means that for every epsilon, blah, blah, blah. So, and every epsilon, there exists, okay, for a sequence to converge, that means for every epsilon, there exists that capital N so that we're within epsilon. Okay? Let me write it this way to emphasize that capital N is allowed to depend on both epsilon and our point x. And then what do we want? We want that. Okay, so we just unpacked one level of the definition here. Are there any questions before we go on and look at some examples?
I'm maybe a little bit confused why we call it pointwise if we're saying it's for every x in it. So, like, pointwise would maybe make sense if we said that it was pointwise for some particular point x that was A, but not for every x in A.
Pointwise might make more sense when you see the second definition, but let me tell you why it's pointwise now, and then you'll keep that in the back of your mind. It's pointwise because at every point, we converge. Okay. It doesn't say anything about. Well, okay. So I mean, what's going to change in that second definition is that we're not going to allow our capital N to depend on the point.
Okay.
Okay. So in this definition, it's convergence at every point. In the other definition, it's going to be actual convergence, like together at the same time.
Okay.
Okay, but really the only definition, the only change is going to be we're going to move a quantifier and we're not going to allow that the capital N to depend on x. Okay, let's look at some examples.
Is the difference that one is just weaker than the other, or?
Mm-hmm. Yeah, this is the weaker one. Okay. Now I'm gonna be lazy. I'm gonna use examples out of the book with the same in the same order. So this will be example A. Define your functions to be x over n. Okay, Fn is a sequence functions from, what's the domain here? Well, what's the largest domain we could take?
R.
Mm-hmm. And does this converge to anything? Does this sequence of functions converge to a particular function? Well, let's look. Let's look at the limits that we're going to get. Okay, if I fix an x, what is that limit going to be?
Should be 0, right?
Yes. Okay, and that's the point. In pointwise convergence, the x is fixed. Only the function changes. Okay. So let's see. This sequence does converge to the 0 function. Okay? Now, example B is more interesting. Our functions are x to the n. Let's do the same analysis in the same order. This is a sequence of functions from, what's its domain? Well, the largest possible domain.
The reals.
Mm-hmm. Now let's look at the limits. Again, we're thinking about x as fixed. What do you know about that limit? I don't know how. I don't know if we've actually proved things about this limit in this course, but you can just use your intuition as well.
Doesn't it depend on whether, we'll say, x is between 0 and 1, and whether x is greater than 1?
Mm-hmm. Yeah, so, okay, let's do x. Well, and we're allowing x to be negative too, right? Okay, so when is this limit 0?
If the absolute value of x is less than 1.
Mm-hmm. I like that. I'm going to use interval notation instead.
Okay.
Okay, what other values can this limit take?
One.
Mm-hmm. When is that?
Definitely when x is 1, but I have to think a little bit more about -1.
Okay, go ahead and think a little bit more about -1.
I would say it doesn't converge for negative numbers greater than or equal to -1, because positive powers, it's a positive number, negative powers, it's a negative number.
Yeah, it's our classic non-converging alternating sequence. So -1, -1, 1, -1, 1, -1. So when x equals -1, the sequence of functions does not converge. And if the absolute value of x is bigger than 1, then it certainly does not converge, because the absolute values just get bigger and bigger. Okay. So, this sequence of functions does not converge on its entire domain. But if we restrict the domain, then it does converge. So that's what we're going to do. We're going to say that on, let's see, that interval, open at -1 to closed at 1, this sequence converges to the function f. Well, I'm just going to copy that function down again. Okay.
So just to be clear, the sequence of functions fn only converges when we restrict the domain of fn to be -1 to 1 open quotes, right?
Yes, precisely. Yeah. Even though fn is defined, each of those functions is defined on all the reals, we have to restrict the domain to get pointwise convergence.
Because if x is like if it's 1.001, even if it's that little bit over 1, as n increases, it's just going to explode.
Yep. Yep. Exponential growth, which some people have said is the term of the year. Okay, so in the book there's a few more examples. I want to skip those examples because I want to get to the other definition. Okay. Let's just jump into the other definition. So this is.
So if there's a single point in the domain where it doesn't converge, do we say that function is not pointwise convergent?
Well, okay, so if there's a single point where the sequence of functions does not converge, then I guess, yeah, we would say that sequence of functions is not pointwise convergent, but in practice we would probably restrict the domain, like we did in example B.
Okay, that's helpful, thank you.
Okay, good. Okay, so here's the stronger and better definition. So what happens, and you can look at examples, and we'll see some more examples, especially in our last two lectures. If you know a sequence of functions converges pointwise, that doesn't really tell you anything about the limit function. However, with the stronger definition of convergence, which is what everybody suggested at the beginning of class, you actually can conclude things about the limit function. So here's the stronger definition. Instead of just insisting that we converge at every point, we insist that we converge at every point, but also kind of at the same rate, or at a similar rate, kind of. So here's the definition. So, let's see, how did we state the other definition? We said, you know what, let me attempt to do this. Oh, No, that's not how I do it on this app. Ooh, so far it's working. Oh, so far it's working. Okay. That's the restatement of the pointwise convergence. Now, let's state the other definition. You've still got a sequence. And our new term is that it converges uniformly. Now, it's very important to keep. We have two very similar sounding definitions. One is uniform continuity, the other one is uniform convergence. Very important to keep them separate. Just remember that uniform continuity is a property of a single function, whereas uniform convergence is a property of a sequence of functions. Okay, but the same word shows up in both definitions, and really what that the word uniformly means is just that we can move the quantifier, right? So instead of the thing depending on the point, it now is not allowed to depend on the point. Okay, so it converges uniformly on F if for every epsilon let me parallel the statement above. If for every point no, I don't want to do that. I want to say for every epsilon. There exists, and I'm not mentioning the point. There exists a capital N, which we haven't mentioned a point, so it can't depend on the point, such that now I'll say for every x. Okay. That's the difference between converging pointwise and converging uniformly. Is the capital N allowed to depend on the point you're looking at? Yes or no? Those are the two definitions. So I hope it's obvious that if you converge uniformly, you're also going to converge pointwise. Because that single capital N will now work in the pointwise definition no matter what the point x is. Okay. Now, let's go look at our examples. And now, okay, I moved stuff around. Never mind. We're going to still look at our examples, but we'll rewrite them. So this example was x over n. Is that convergence uniform? Oh, sorry. And we know Fn converges pointwise to the zero function. And I realized there's something I wanted to say up here. Because the question I want to ask is this convergence uniform? Well, you might ask, does it have to converge to the same function? So here's a fact / proposition / lemma. If your sequence converges pointwise, no, I'm sorry. This is what we said. If it converges uniformly to F, then it converges pointwise to F. Okay.
I also imagine, since the definitions are so similar, we get all of the same uniqueness of limits and whatnot.
Oh, I guess I should have said something about uniqueness of limits. Yeah, so you think about the pointwise definition. If those limits exist, they're unique. So you can only converge pointwise to one function. And then this fact is what we need in order to say you couldn't converge uniformly to a different function than you converge pointwise to. Okay? But really we can say something stronger than this. Because we know the uniform definition is stronger than the pointwise definition. The domain of convergence uniformly could only be smaller than the domain of convergence pointwise. Okay. Okay, so now the point is, because of this fact, since we know this sequence from example A does converge to the zero function, we can say, is that convergence uniform or not? So, any volunteers?
I would say no, because it seems to me that for any n, we could pick x to be so massive that x over n is not even, it is way bigger than epsilon.
Yes. So now we just have to carefully negate this definition and prove this, right? It's actually a lot like the last question on the quiz that you're going to get back after class, where again we just have to carefully negate this definition. So if we're negating the definition, we get to pick an epsilon. Let's let epsilon be I don't know, 1/2. Okay. And now we have to prove it for all capital N. Now what do we want to prove? That this inequality doesn't hold for some capital X. Sorry, not capital X, for some X.
So do we only need to show that it's not uniform? We only need to pick one lowercase n and one x, because then it breaks the for all. So we only need to find one of these examples, or do we need to find a whole family of them?
Right. So we get to pick the epsilon. We have to disprove it for every capital N, but for every capital N, we get to pick a new x. Okay? So what x would we pick to make this inequality be false? So I want to say if we set little x equal, and I'll leave a blank, then fn of x minus f of x equals, now what will it equal? It'll equal x over n minus f. F is the 0 function, so minus 0. And then that'll be presumably greater than or equal to something. And then we'll have that be greater than or equal to epsilon. This is what we want. What should we set x equal to? So something really big, right?
We could pick n epsilon.
Mm-hmm. And I should have written then for all little n greater than or equal to. Oh, no, sorry. Actually, capital N by itself does it. And what I really want to put here is actually an equals. No. Okay. Now, it's worth unpacking this definition a little bit more. And the book does this in a lemma. 8.1.5, which is that they say sequence Fn does not converge uniformly to the function f if for some epsilon naught, that's the epsilon we get to pick, there is a subsequence fnk. It's a subsequence of functions and a sequence of points. Oops. So I want to write that as a sequence of points. Such that for all k, our inequality goes the wrong way. Okay. Again, this is like the restatement of the pointwise convergence. This just follows from carefully thinking about that definition. So there you go. Putting the lemma and the definition on the same screen. In our example, our subsequence f and k was actually the entire sequence, and our points xk well, here, let me write it this way. if we do this, then f nk of xk equals k over k equals 1. That's what we did in our example. Okay. Let's try this again in our second example, which was x to the n Now, we're going to consider this only where it pointwise converges. Okay, because where it doesn't converge pointwise, it's definitely not going to converge uniformly. Again, that just follows because uniform convergence is a tougher definition. This converges to this function now. Is that convergence uniform? Let's use our lemma again. Whoa, so that gives it away. It's not uniform convergence. How do we get that out of our lemma? Well, let's take our subsequence. So let me emphasize in this lemma, you're allowed to take a subsequence of the functions, but you frequently don't need to. You frequently just consider the entire sequence. Okay, so let's take our nk's to be k, which means we're considering the entire sequence of functions. So for each function fk, we want an xk. Oops. We want a definition of a xk that will make the nk's are k. We want to make this greater than or equal to epsilon naught. And we get to pick the epsilon naught. Okay, and what's this going to be right here? This is going to be xk to the k. And then we're going to have a minus f of xk. And we're going to want this to be at least epsilon naught. So I'm writing this right in a very nonlinear fashion. This is just scratch work, and we would have to write the proof afterwards. But any thoughts?
We could have xk equals x to the minus k, and then those exponents cancel out and we're going to get 1 every time. Seems useful.
Exponents don't cancel out that way.
Oh, oops.
So let's notice first that as long as xk is not 1, we get to ignore the f of xk. That's going to be 0. So this is 0 if xk is not equal to 1. And we get to choose xk, so let's just not choose it to be 1. Okay.
Well, I don't know what Daniel was saying. What if you did x to the 1 over k? And
Yeah.
the exponents could cancel?
Yep, but better, we shouldn't have an x there because it's up to us to pick x. So let's go one step better.
1/2 to the 1 over k?
Yeah. Okay, so all I'm saying there is instead of saying like for any x, right, we should just pick the x. Okay, so we make it 1/2 to the 1 over k, and then when we come over here and plug in, we'll get 1/2 to the 1 over k to the k, which is just 1/2. So we can take our epsilon naught to be 1/2.
I have a question about this style of disproven.
Mm-hmm.
So we're finding just, one simple counter example. Is it at all useful to say like how non-uniformly convergent the function is, or the sequence of function is? Because maybe we picked only the one. I don't know. I don't know if you. I think you understand what I'm saying.
Yeah, I mean, so there might be a like smaller domain on which we could prove uniform convergence, and so we might want to toss out some of our points because they would just, okay, we're not uniformly convergent over there, but we are uniformly convergent here. That might happen, but in general, no, there's no like measure of uniform convergence. The sequence of functions either converges uniformly or it doesn't.
So we don't really care so much about how much it is.
Right.
Okay.
Okay, so that's our lecture for today. We got through the two definitions. Let me emphasize, this is kind of a big point. The second definition is much more useful. The reason we keep the first definition around is because it's a lot easier to see what your sequence of functions converges to in the first definition. So you use the first definition, you say, I'm just going to look at pointwise convergence, and you get what your sequence converges to pointwise. And then you ask, is that convergence uniform? Okay, so if we go back up to this fact, right, this fact is why we keep both definitions around. Because frequently you'll look at the sequence pointwise to find out what it could converge uniformly to. Okay? Because if I just gave you a sequence out of the blue and I said, does this converge uniformly? It's hard, if I just say, does it converge uniformly? It's hard to go through that definition and prove that it doesn't converge uniformly to something. Okay, in all of our examples, because we knew what the sequence had to converge to, because we already knew the pointwise answer, we were able to go through that definition and say, oh, well, it doesn't converge uniformly to that. Okay, I hope that makes sense. You get what it has to converge to from the pointwise definition, and then you ask, is the convergence extra nice? Well, that's annoying. Okay, so that's the end of the lecture for today, and like I said, I'll have office hours later this afternoon.